morning, students. In previous class, we have seen structure of coordination compounds with the help of valence bond theory. In that first example, we have seen. Okay, now let us see that first example once again. CO NH36 plus 3. CO NH36 plus 3. This is the example we took. Okay, now oxidation number of cobalt is plus 3. Yesterday I explained already. Directly I am writing the electronic configuration of CO plus 3, that is argon argon 3D, 1 minute, iron cobalt 27, 3 electrons are removed, 3D, just 1 minute. 3D6, 4 is 0, 4p 0, 3D6 electrons. Initially it is contained by 1, 2, 3, 4, 5, 6. Like this it is contained according to Hund's rule. Now 4 is 0, 4p 0. Okay, now what is going to be happen? The electrons which are present here, this fifth electron is going to be paired with third electron. Fourth electron is going to be paired with second electron. Then the electronic configuration will be becoming like this, and 4s0, 4p0. These orbitals will be remain like this. Now it will undergo which hybridization? D2 sp3 hybridization. Okay, see, d orbitals, 2d orbitals. Those 2d orbitals are from 3d. Those 2d orbitals are from 3d. 3d means this is n-1d, inner orbital, inner d orbital. Next, this is ns, this is np. D orbitals are not involved in hybridization from outer orbital in this complex. Okay, they are involved with inner d orbitals. That's why this complex is called inner orbital complex. Inner orbital complex. Next, previously, if Hund's rule is followed, okay, how many unpaired electrons are present? 1, 2, 3, 4. 4 unpaired electrons are present. Now VBT is explaining that this electron is going to be paired with third orbital electron, fourth electron is going to be paired with second orbital electron. Pairing is taken place. Because of that, spin is getting reduced. Spin of the electron is getting reduced. This spin, previously 4 half spins are there. 4 half spins are there. Now one spin is cancelled with another spin. Both are in opposite direction, they are getting spinning. Correct or not? This is in clockwise direction, this is in anti-clockwise direction. What happened to spin? Cancelled. Because of that, spin is getting lowered. That's why this is also called low spin complex. This is also called low spin complex. Okay, so what are the names? Inner orbital complex. Why this is called inner orbital complex? Okay, this is because inner 3d orbitals, outer 4s 4p orbitals are involved in hybridization. That's why this is called inner orbital complex. Next, why this is called low spin complex? Previously unpaired electrons are present, but valence bond theory explains that pairing will be taking place. Because of the 3D empty orbitals are getting available. Okay, this pairing is taking place in which spin of the electrons are going to be reduced. Spin of the electron is going to be reduced. Then it will become low spin complex. Okay, which hybridization is undergone? D to sp3. D to sp3 means yesterday I have drawn the structure. Structure is octahedral. D to sp3 hybridization. D to sp3 hybridization. Inner orbital complex. Low spin complex. Structure is octahedral. Okay, and coming to magnetic nature. Coming to magnetic nature, this is diamagnetic. This complex is diamagnetic because it has no unpaired electron after the involvement of the bond compound. After the involvement as compound, okay, it does not contain any unpaired electron. The compound or the substance which does not contain any unpaired electron is coming as diamagnetic substance. The substance or compound which does not contain any unpaired electron. See here. Now, how many empty orbitals are there? No? 6 empty orbitals are there. Nitrogen, NH3. NH3 contains lone pairs of electrons. No? NH3 contains lone pair of electrons. First, one electron is donated into the empty orbital. First, one electron is donated into the empty orbital from nitrogen. After the donation of the electron, here one electron is there, here one electron is there. These two are involved in bond, which is called coordinate covalent bond. Like that, this is going to be involved in bond with another NH3. This is going to be involved in bond with another NH3. This is going to be involved in bond with another NH3. This is going to be involved in bond with another NH3. This is totally 1, 2, 3, 4, 5, 6. 6 NH3 molecules are bonded with CO plus 3. This CO plus 3 is involved with ionic bond with 3 Cl minus ions outside. The CO plus 3 is involved in 3 Cl minus ions outside. These are counter ions, primary valency. Secondary valency 6 empty orbitals. Into the 6 empty orbitals, 6 ligands are going to donate to get octahedral structure. After the formation of the total thing, any unpaired electron is present. So, no unpaired electron is present. If the compound has no unpaired electron, then that substance is diamagnetic in nature. Okay, ma'am? Now, once observe this, all of you. All of you see to that carefully. I hope you are clear about this. Okay, ma'am? Observe the following example, CONH36 plus 3. Outside counter ions I wrote Cl3. Okay. Without counter ions if I write, we will write on square bracket plus 3. Okay, I hope you are clear. Now, what is meant by diamagnetic substance? Okay, the substance which do not contain any sort of unpaired electron. Observe this compound, all of you. After the formation of the compound, okay, it does not contain any unpaired electron. NH3 donates one electron into the empty orbital. After that, again that unpaired electron is going to be paired with nitrogen unpaired electron, correct? Then complete bond is formed. That's why this molecule does not contain unpaired electron and it is diamagnetic in nature. Okay, but clarity about this diamagnetic, once again I will explain. Let us see these 4 examples. After these 4 examples, once again I will go through what is the magnetic nature, diamagnetic nature, paramagnetic nature. Okay, first remember, the compound which does not contain any unpaired electron, it is diamagnetic in nature. If the compound has any unpaired electron, 1 or 2 unpaired electrons, or 3 or 4, whatever it might be, that is paramagnetic in nature. Okay, till the completion of these 4 examples, remember like this. Next, inner orbital complex, you got clarity. Low spin complex, you got clarity. structure octahedral, magnetic nature diamagnetic. These are all successfully explained by valence bond theory. Okay, now next example is next B, example B, that is CO F6 minus 3. What is that? COF6 minus 3. Here complex is negative complex, then counterions must be positive counterions. Okay, ma'am? Now let us see COF6 minus 3. How we are going to say? First to find the oxidation number of cobalt. Cobalt oxidation number we don't know. Let oxidation number of cobalt is X. How many cobalt atoms are there? One atom. So it will be 1. 1 into X plus 6 into, what is the oxidation number of fluorine? Minus 1 is equal to, what is the charge present here? Minus 3. This square bracket has minus 3 charge. Okay, so X minus 6 is equal to minus 3. X minus 6 is equal to minus 3. X is equal to 6 minus 3, that is plus 3. So what is the oxidation number of cobalt? Plus 3. In previous example, what is the electronic configuration we wrote for CO plus 3? Same electronic configuration we will write here again. Okay, now let us see. I am going to write the electronic configuration of CO plus 3 directly. Argon 3d6, 4s0, 4p0, 4d0. Okay, 3d6. 1, 2, 3, 4, 5, 6 electrons. Empty orbital. 3 empty orbitals. 5 empty orbitals. Okay, now to explain this one, in previous example we have seen that this electron is going to be paired with this one, this electron is going to be paired with this one, like this. But in this example we will not consider pairing. This electron is not going to be paired with this one, this electron is not going to be paired with this one. Okay, but instead of these inner orbitals, this cobalt plus 3 in COF6 minus 3, it will use 4D empty orbitals. Instead of 3D empty orbitals, it will use 4D. Here 3D does not contain any empty orbital. Is it correct or not? 3D does not contain any empty orbital. All are completely filled. But you can ask me immediately, in previous example what we have done? In previous example what we have done? Same thing if you have done here, then it is possible with inner d orbitals also. But we should not do like this. Reason, after completion of this example, I will compare these two molecules and I will explain. Is it okay, ma'am? First, how it is undergoing, let us observe. Now let us see. 4s0, 4p0, 4d0. Now 1s orbital, 3p orbitals and 2d orbitals. 5d orbitals are available, but maximum that d2, 2d orbitals are only involved in hybridization up to d, 2d. Then it will be sp3d2. Observe. In previous example, I wrote hybridization d2sp3. Now I wrote sp3d2. Observe the difference. Now this is NS, NP. Even this is also ND. All are outermost configuration. All are outermost orbitals only. All are outer orbitals. See 4s, 4p. These are involved in hybridization with 4d. Outer orbitals only na? That is. Now this is called outer orbital complex. Now this is called outer orbital complex. Now hybridization sp3d2. Structure, same structure, octahedral. Okay, see. Here F, this coordinate covalent bond F minus 1, it will be involved in coordinate covalent bond with this orbital. Same F, coordinate covalent bond F from above. These four are in plane. This is above the plane and that is below the plane. Structure octahedral. Octahedral. Okay. So this is involved in bond with F minus F coordinate covalent bond with F minus. Like this, all the 6, 1, 2, 3, 4, 5, 6. 6 fluorines are involved in bonds with 6 empty d orbitals. Hybridization sp3d2, structure octahedral, but previous complex is our inner orbital complex. This is outer orbital complex. Okay, now these electrons are not involved in pairing, na? That means pairing is not decreased, spin is not decreased. So this is high spin complex. In previous example, electrons are getting paired. That's why spin is reduced. Because spin is getting cancelled, na? Positive spin and negative spin, they are getting cancelled. But here that cancellation is not happening. So 4 unpaired electrons are present. High spin complex. How many unpaired electrons? 4. This is paramagnetic. If unpaired electrons are present after the involvement in bond, we will get paramagnetic nature. That substance is in paramagnetic. Okay? Just once see this one carefully. This is the information about COF6 minus 3. Okay. Now the problem here is, in previous example, why these electrons are getting paired. In this example, why these electrons are not paired. That clarification was not given by valence bond theory. That is the drawback of valence bond theory. That is the drawback of valence bond theory. That is clarified by crystal field theory. Next theory we will study one more theory, which was called crystal field theory, CFT. In that CFT, why that previous example CONH36 plus 3. In that CO plus 3, pairing is taken place in CO plus 3. In this complex, why this pairing is not taken place, you will get clarity in crystal field theory. That is remained as drawback for valence bond theory. So after completion of this theory, we will see the drawback of valence bond theory as this one. Okay, but by pairing like that and remain like this valence bond theory could explain correctly the magnetic properties of the compounds. Okay, magnetic properties were explained correctly by valence bond theory. Okay, ma? Now let us see the comparison between first compound and second compound. Once like a revision means recall like that I will show. I am going to rub this one, ma? Observe all of you. Once observe this diagram and everything on board. CONH36 plus 3. This compound COF6 minus 3. Okay, cobalt plus 3. Electronic configuration directly I am writing here. Argon, (3d6). 1, 2, 3, 4, 5, 6. 4s0, 4p0. D2sp3. D2sp3, violating Hund's rule. Okay, next, inner orbital complex. Inner orbital complex. Next, low spin complex. Low spin complex. Next, structure octahedral. This is not contained by any unpaired electron, then this is diamagnetic in nature. If the substance does not contain any unpaired electron, then it is diamagnetic in nature. Okay, observe correctly. CONH36 plus 3. Regarding that, what is the useful data I wrote on board. Okay, next. I'm coming under COF6 minus 3. Configuration CO plus 3 configuration. Argon 3d6, 4s0, 4p0, 4d0. 1, 2, 3, 4, 5, 6. 4s0, empty orbital. 4p0, 3 empty orbitals. 4d0, 5 empty orbitals are available, but it will use only up to 2 more. Then this is sp3d2 hybridization. This is d2sp3. This is sp3d2 hybridization. 3d6 as it is I wrote. Here pairing is taken place. Okay, that's why following Hund's rule. If it follows Hund's rule, outer orbitals it will use. That's why this is outer orbital complex. Next, these are remained as half spin solenoid. That's why this is high spin complex. Next, structure same structure only, octahedral, but contains 4 unpaired electrons. No? It is paramagnetic nature. So till now the 2 examples whatever I discussed, the important points I wrote it on board. Just note down like this, like a comparison, it will be useful for you. Okay. But one more clarity, in CONH36 plus 3, why those are involved in pairing, and in COF6 minus 3, why those are not involved in pairing. That clarity was not given by valence bond theory. Again I am telling. That's why that point we will not discuss. That point we will discuss in crystal field theory, CFT. Why these unpaired electrons involved in pairing in CONH36 only, but those are not involved in pairing in COF6 minus 3. Okay, but this type of explanation was given by valence bond theory by following practical results. That practical results now I will show on board. Okay, ma? I am going to rub these 2 datas but I will keep the examples like that only. And under that I would like to mention magnetic property. Left hand side this is diamagnetic in nature, right hand side this is paramagnetic in nature. Okay, let us show that one. These two compounds, they will be undergone one practical thing, that is magnetic susceptibility. This procedure is magnetic susceptibility. Okay, by using that procedure we can find directly the magnetic moment of the compound. This is the experiment, man. Magnetic susceptibility experiment. By using that experiment, directly we can find magnetic moment of the compound. Magnetic moment means we can estimate the magnetic nature by using that value. By using this magnetic moment value, we can estimate the magnetic nature. Okay, that is found or measured by using the experiment, that is magnetic susceptibility experiment. Okay, by using this one, magnetic moment is represented by mu. Mu is equal to 0 for this complex. Okay, man. Now mu is equal to some 4.87 like that. Bohr magneton. Bm means Bohr magneton. Units for magnetic moment. Okay, Bohr magneton. What is the mu value for COF6 minus 3? That is 4.87 Bm. What is the mu value for CONH6 plus 3? That is 0 Bm. Okay, and as well as one more formula is there, that is mu is equal to root of n into n plus 1. Mu is equal to root of n into n plus 1, which was derived by scientists theoretically, where n is called number of unpaired electrons. Where n is called number of unpaired electrons. Okay, so if you know the mu value, by using the practical experimental value, that is magnetic susceptibility procedure, we will get magnetic moment value, mu value. By using that we can find unpaired electrons. Number of unpaired electrons we can find. Are you able to understand? Now see, left hand side mu, right hand side 0. Now let us equalize both of them. Root of n into n plus 1 is equal to 0. N into n plus 1 is equal to 0. N is equal to 0. How many unpaired electrons are present in this compound? 0 unpaired electrons. Next, coming to here, 4.87 is equal to square root of n into n plus 1. Then 4.87 whole square is equal to n into n plus 1. If you solve this one, you will get n is equal to 4. Definitely you will get n is equal to 4 or approximately. Okay, this is mentioning that in this compound, how many unpaired electrons are present? 4 unpaired electrons. In this compound, 0 unpaired electrons. This is experimental value only. To satisfy this experimental value, this theory wants to explain this model by pairing of electrons. By pairing, 0 unpaired electrons are present. This is coming under diamagnetic. If 0 unpaired electrons are present, that is diamagnetic. If any one unpaired electron, 2 or 3 or 4, if they are present, then this is paramagnetic. In this way, valence bond theory, for this one, pairing is taken place. It took the help of pairing to explain zero unpaired electrons. In this one, it doesn't involve in pairing, it follows Hund's rule. Then we will get 4 unpaired electrons. You have seen the previous tabular column, one subsummer, 4 unpaired electrons. Correct or not? Then this is satisfied explanation. This is also satisfied explanation. But immediately remaining scientists, they will get a doubt. That is, why in this compound only pairing is taken place? Why in this compound pairing is not taken place? Why this is inner orbital complex? Why this is outer orbital complex? Like that clarity, they asked the question. But valence bond theory could not explain that one. That one in next theory, that is CFT, we will see. I will give clarity about that one. But this total information was given correctly by valence bond theory. According to this, 0 unpaired electrons and 4 unpaired electrons successfully explained by valence bond theory. But why that pairing is taken place, that one was not explained. That is the problem here. Okay. But anyways, some explanation was given, correct or not? That is. So see this one carefully, all of you. I hope you are clear now. First compound diamagnetic in nature, second compound paramagnetic with 4 unpaired electrons. This is experimental data. That experiment procedure is magnetic susceptibility. By using that magnetic susceptibility, we can find the magnetic moment of the compound. So first compound magnetic moment mu is equal to 0. Second compound magnetic moment mu is equal to 4.87. Okay, this is about complete information regarding first two examples, which are examples for octahedral structure. Now we will see coordination number 4. In these two compounds, coordination number 6 ma. Okay, now let us see next coordination number 4 examples. Next, third example, that is C. NiCl4 minus 2. This is the next example. Okay, first let us find
monthly earnings by selling trending products online.
This is the next example, that is NiCl4 minus 2. Okay, in this first we want to find the oxidation number of nickel. Okay, now let oxidation number of nickel is X, 1 into X, because 1 nickel is there, plus 4 into chlorine minus 1 only na, is equal to total complex charge minus 2. X minus 4 is equal to minus 2. X is equal to 4 minus 2, that is plus 2. So what is oxidation number of nickel? Plus 2. First, let us write the normal electronic configuration of nickel. Neutral atom nickel electronic configuration. Argon 4s2 3d8. Next, Ni plus 2. Okay, ma'am? Configuration. Argon. These 2 electrons must be removed. Those 2 electrons are removed from 4s only. Then this one will be 3d8. And 4 is 0. 3d8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 4 is 0. 4p0. In this, pairing is not taken place following Hund's rule. Then what is going to be happening? This 1s orbital and 3p orbitals will undergo hybridization, sp3 hybridization. In this, we will not say whether it is inner orbital complex or outer orbital complex, because anyways in this complex, d orbitals are not involved in hybridization. Only s and p orbitals, that is sp3 hybridization. Correct? That's why we will not say inner orbital or outer orbital. Okay, but this is high spin complex. High spin complex, hybridization sp3, structure tetrahedral. Structure tetrahedral. This is the information about NiCl4 minus 2. We will follow Hund's rule. Magnetic nature, important. 2 unpaired electrons are there. Then this is paramagnetic in nature. If the compound has unpaired electrons, then it has definitely paramagnetic in nature. Okay. These empty orbitals are filled with Cl minus coordinate covalent bonds. That much no need. Simply this, if you write the structure, it is enough. No need to draw. Like in chemical bond, here no need to draw. Okay, ma? This is information about NaCl4 minus 2. Once again, I will write like a comparison. No problem. Just observe. After that, immediately I will go through fourth example. Okay, ma? Fourth example is NiCN4 minus 2. First oxidation number of nickel X minus 4 is equal to minus 2, X is equal to plus 2. So Ni plus 2. Directly I am writing Ni plus 2 configuration, that is argon 3d8 1, 2, 3, 4, 5, 6, 7, 8, 4 is 0, 4p0. Okay, but this compound directly, if it undergoes susceptibility experiment, we will get magnetic moment 0. 0 means number of unpaired electrons 0. Then to explain that 0 number of unpaired electrons, this valence bond theory took the help. That is, this electron is there, na? It is going to be paired with this electron. Then it will become 3d8 only. 1, 2, 3, 4, 5, 6, 7, 8. Okay, violating Hund's rule. Okay, violating Hund's rule. Then here 4 is 0, 4p0 are there, na? It is coordination number 4, means it should be involved with 4 orbitals hybridization. Then 1d orbital, 1p orbital, 1s orbital, and 2p orbitals will undergo dsp2 up to here only. Which hybridization? dsp2. dsp2 means immediately shape square planar. Shape square planar. So this is low spin complex because pairing is taken place na low spin complex. dsp2 hybridization, square planar structure. Any unpaired electron is present? No unpaired electron. Then this is diamagnetic in nature. This is fourth example. NiCN4 minus 2. All of you observe now. Okay, I hope you are clear about these four examples. In next class, I will compare C and D examples. How that is high spin, this is low spin. Hybridization, once again I will discuss. Okay, structure, tetrahedral square planar. Next, diamagnetic, that is paramagnetic, this is diamagnetic. Once like a correlation, I will show these C and D, third and fourth examples now. Okay, I think this is about today's class. You are very clear about what is explained. Same thing, in fourth example, that pairing is taken place. In third example, pairing is not taken place. That clarity was not given by valence bond theory. But these two, according to paramagnetic nature and diamagnetic nature, they are explained correctly by valence bond theory. Okay, ma'am? Little bit more explanation about this third example and fourth example, I will go through in next class. Okay? All of you, I hope you are very clear about this one. Thank you all.